hello, and again, and a warm welcome from my side. It's a pleasure to have the opportunity to introduce the VISION-xEV project and the recent results we have achieved. Let me first start with a short overview on the project itself. So as Alain has already outlined, it's one of the projects submitted and funded under the GV02 2018 scheme. The full name is Virtual Component and System Integration for Efficient Electrified Vehicle Development. And it started actually in January 2019 and will end by end of December this year. The project is conducted or carried out by 14 partners from all over Europe with a budget of close to 4 million euro, and it's coordinated by AVL. So regarding the consortium itself, it's of a well-balanced composition of partners from the vehicle industry, from FPT, from Central Research Fiat and Group Renault. There are 3 software and hardware suppliers participating in there, and a number of universities and research organizations that contribute with their outstanding expertise on modeling, simulation, also experimental characterization. Well, the overall objective is to support the acceleration, speeding up of development activities related to all kinds of electrified and hybridized vehicles, with a focus on the activities on the left-hand side of the V cycle. So in the concept phase, in the component development phase, and on the virtual integration phase. And with this, the project strongly focuses on component modeling and simulation, and especially on the virtual testing aspect, on integrating the individual component and subsystem models to virtually represent the system, and helping thus supporting shifting of development activities from towards earlier phases in the development, and also helping to shifting development activities from the lab towards the office world. Well, this overall objective within VISION-xEV leads to a number of specific technical objectives we identified in the proposal preparation phase, and we're addressing in the course of the VISION-xEV activities. So it's by bringing down, reducing the experimental effort required to parameterize specific component behavior, and to derive and parameterize the corresponding simulation models. So so that's one focus of activities, and another strong focus is on developing, elaborating methods and tools and workflows to enable seamless coupling of the individual component and subsystem models in order to enable their co-simulation, in order to being able to efficiently and in a fast manner to build up digital twins of the entire powertrain and vehicle system, and to support stable and robust, efficient simulation of the system behavior under real-world driving conditions. And all these aspects together are also supplemented by increase in model prediction accuracy, which is also a central point of the activities. So increasing prediction accuracy on a component level, and then where suitable co-simulation methodology is also on the system simulation side. The activities were strongly focusing, or have been focusing, on the different components and subsystems of electrified powertrains, and let me give you some overview of highlights that have been achieved in the course of the project. And there was one strong focus on the modeling and simulation of the electrical energy storage components and systems in order to facilitate an efficient experimental characterization of the behavior of the battery and supercapacitor cell on a laboratory scale. And here VUB and CNR carried out a comprehensive set of activities in order to reduce the effort in experimental characterization of the electro and thermal behavior of battery and supercapacitor cells, which then served as input to parameterize corresponding simulation models representing the cell characterization for further usage then in the context of detailed 3D simulation of the multiphysical behavior of an electrochemical battery and supercapacitor cell in the context of battery module and battery pack, and to use this information then also to parameterize fast system level models for use in the context of an overall system simulation views of the in order to support development activities related to battery management system, battery thermal management, so cooling, heating up during real driving cycles, during charging cycles. And that activity finally led to a significant reduction in the cell characterization effort and in the effort to parameterize reliable and predictive simulation models. As a second decisive component of electrical powertrains, VISION-xEV has been also focusing strongly on the electrical energy conversion of electrical energy into mechanical energy, and we had a dedicated work package focusing here on modeling and simulation of electrical machines and the related power electronic component. Also in terms of a multiphysical view in order to involve all the relevant aspects, electrical, thermal, mechanical aspects into the simulation activities. So detailed 3D simulation methodologies have been advanced and optimized in order to enable a detailed insight into the electrothermal characteristics of power electronic and e-machine components. And strong focus was put here also on methods to use detailed 3D information in addition to experimental data to parameterize or to build up and parameterize high fidelity system level models of the different kinds of electrical machines and with a strong focus on induction machine and externally excited synchronous machines. So the major outcome of these activities carried out by University of Ljubljana, AVL, Thermal and HVAC, faster high fidelity system level models have been built up and established and enable with a largely reduced effort in parameterization and model setup effort, multi-physical representation in the context of system simulation applications. Well, besides that, also some effort has been spent on updating and refining existing models on the internal combustion engine side and related turbocharging and after-treatment component modeling side in order to support different kinds of hybrid vehicles, with a specific focus on plug-in hybrid vehicles, especially with respect to the after-treatment side, where the plug-in hybrid vehicle operation modes leads to quite some challenges regarding keeping the temperature of the exhaust system at sufficient high level during all driving operations. So ensuring that the conversion efficiency during real driving cycles is always kept on a very high level, which will bring also additional and new technologies with respect to phase change material or electrically heated catalysts. And these new technologies, models and related parameterization methods have been developed, as well as the coupling strategy to have the different the IC engine models and the after-treatment models to seamlessly work together in a highly accurate and highly efficient manner. So here the Polytechnical Milano was focusing on the IC engine models and the integration activities of models from TIL Berlin and KDH on the turbocharger side, as well as models for the after-treatment system provided by University of Thessaloniki and thermal engine management system models contributed by University Valencia. So in this area, significant increased model predictive accuracy could have been achieved together with findings and achievements regarding a robust coupling of the different models acting at largely different time and length scales. And as a major activities in the second half of the project, these component and subsystem models were coupled and linked together, and for this purpose, interfaces have been defined in order to get a realistic and reliable physical representation of the interplay of all the individual components in electrified and hybridized powertrain systems, models that are originating from different partners, from industry partners, from academia, models that are based on different modeling platforms, different commercial software tools, in-house tools, and these interfaces were defined in mutual interaction with all the partners, and were used then in the implementation activities, in building up the overall simulation framework to ensure that all the individual models can seamlessly work together and can work in a robust, numerically efficient way, so to represent flexibly all different kinds of electrified and hybrid powertrain systems. And so here the AVL activities were strongly focusing on the system architecture aspect during the concept phase. Politecnico Milano, University of Valencia, TU Berlin, and University of Thessaloniki, they were focusing on the coupling of the thermodynamic part of hybrid and electrified powertrain systems to support efficient engine after treatment system coupling for applications under real drive cycle conditions with close to real-time performance in order to predict tailpipe emissions during WLTP cycles, during all different kinds of real drive cycle conditions, and to support the evaluation of engine start and stop impact on fuel consumption and emissions. In order to properly account for the thermal aspect of the entire powertrain and to also include aspects of vehicle cabin heating, ventilation, air conditioning system, and specifically to address different concepts of powertrain component subsystem cooling, thermal management, thermal conditioning of hybrid electric vehicles and specifically of battery electric vehicles. The AVL Thermal and HVAC established and built up a framework for a holistic vehicle thermal management system with open interfaces to seamlessly integrate and couple battery models, supercapacitor models, engine models from the different partners into this thermal management view, to being able to deal with aspects of transient powertrain and vehicle cabin heat up, to enable a flexible, holistic thermal analysis of battery transient heat up during different ambient conditions, during different drive cycle conditions, and also to provide the basis for an integrated thermal management control function development. So this control function development and control framework aspect on the entire powertrain context was dealt with by University of Valencia with dedicated activities aimed at providing a platform for optimization of electric and hybrid vehicle energy management related tasks. In this context, the framework was built up and validated based on experimental measurements carried out on the test bed, and the applicability was confirmed for different analysis and optimization tasks with respect to fuel consumption of different powertrain configurations for real-world driving cycle under different battery state of charge constraints. And yeah, and in order to have a sound basis for model and model coupling validation, real-world driving cycles studies were carried out by University of Thessaloniki and CNR with different hybrid electric vehicles, and supplemented or supported also by virtual testing activities in order to reduce the number of real world driving tests to be carried out. So with this joint testing and simulative approach, it was possible to reduce the number of real world tests to around 25 and to carry out another additional, a large number of additional cases and mission profiles based on pure simulation, which finally resulted in about 35% reduction on the testing effort. And so based on these activities, it was possible to analyze different real drive cycles to evaluate the impact of different parameters on the whole plug-in hybrid electric vehicle performance and subsystem operation, and also to derive generic representative driving profiles in order to being able as a or to serve as a cross-reference among the different validation and demonstration activities within the project. And yeah, these validation and impact assessment and demonstration activities of to prove the applicability of the modeling and simulation framework set up by the VISION-xEV project. This demonstration impact activities were carried out on the basis of 4 selected industrial use cases or use case clusters, so to say, that were related to aspects like battery system thermal management. There were use cases related to plug-in hybrid vehicle and engine after-treatment system matching for real driving cycles, activities related to vehicle architecture and concept design analysis for different kind of vehicles, and use case 4 was related to the hybridization of a 12-meter urban bus, and to assess and to provide results for assessment of the impact of the VISION-xEV achievements onto the development processes and onto the effort reduction and time reduction of different development steps and development activities. So on the battery thermal management system side, for the partner CRF in in close interactions with other partners such as VUB, such as AVL, build up a digital twin of a plug-in hybrid electric vehicle, including a digital twin of the entire battery thermal management system in order to look into different aspects of thermal management system development and optimization. In order to prove and in order to set up also the seamless model exchange of the battery cell models with the partners, and in order to prove the interaction of the vehicle model and the battery thermal management system digital twin for the different driving cycles under different ambient conditions. So as a major outcome of these activities, it's already or successfully demonstrated that as a considerable increase in the efficiency in building up the digital twins and in increased efficiency in exchange of models among the partners could already be demonstrated, and activities are still ongoing now towards the end of the project, and it's will definitely should bring additional results on top of what already has been achieved. Well, the AVL use case cluster is concentrated on XEV energy management optimization, and is composed of three distinct sub-use cases. One is focusing on a plug-in hybrid vehicle configuration with a strong focus of matching of the hybrid transmission with the vehicle and powertrain architecture, carried out in a close interaction with the partner ZF and University of Ljubljana, providing the transmission model and the e-machine models respectively. Together with the colleagues from thermal and HVAC, we have been focusing on battery electric vehicle thermal management aspects, building up a digital representation of a battery electric vehicle with two different kinds of thermal management systems, battery thermal and powertrain thermal management configurations, a traditional one and a novel innovative one utilizing heat pump technology. And the third use case is related to a truck application, focusing on aspects of hybridization of a commercial vehicle powertrain with 48 volt and 400 volt technology in order to achieve fuel consumption and energy efficiency optimization for different configurations. So these three sub-use cases are still ongoing and will be used to evaluate the impact of the model achievements and the impact of the VISION-xEV simulation and modeling framework on the development effort, and will highlight the time reduction, time savings that can be achieved by an integrated, holistic view supported by massive simulation activities in comparison to traditional approaches. Yeah, well, as a third use case, we know together with the university partners, as they are University of Valencia, Politecnico Milano, and University of Thessaloniki, are focusing on the matching of the plug-in hybrid electric vehicle powertrain with the post-Euro 6 after-treatment system adopting technologies like electric heating, like phase change material on the after-treatment side in order to achieve a hybrid vehicle operation under real drive cycle and ambient conditions by still utilizing highest pollutant conversion rates under all conditions. And as you can imagine, the entire powertrain model comprises component subsystem models provided by all the different partners, models set up utilizing different modeling platforms, and is hence a benchmark use case for demonstrating the seamless exchange of models, the seamless integration of models of the different partners into the VISION-xEV simulation framework. And yeah, and last but not least, use case number 4 from the partner FPT, which is focusing on bus hybridization, on system architecture analysis, and concept analysis of different hybridization configurations, is based on a defined set of test cases and on detailing different aspects related to the development process in order to work out and to demonstrate here the impact of the simulation framework provided by VISION-xEV on the simulation workload, but also on the front loading potential of the simulation framework in the context of the overall vehicle development process. And yeah, with this, let me briefly summarize the status 2 months before the end of the project. Considerable achievements have been obtained with respect to the electrical energy storage component modeling, superior and innovative component models, workflows, and parameterization methods have been elaborated. Also on the electrical mechanical energy conversion aspect, so on the e-machine and the related power electronic components by utilizing high fidelity 3D multiphysics simulation for parameterizing fast system level models and hence reducing the required input of experimental data for setting up reliable models. On the engine and after-treatment component modeling side, considerable improvements with respect to the predictive accuracy has been achieved. In addition, models have been developed covering future after-treatment system technologies for post Euro 6 application. Models have been set up and is validated for thermal management to cover thermal management aspects on the powertrain level, on electric component level, on entire vehicle system level, and controller model activities now are led to status where automated control parameter optimization for the hybrid vehicle controller can be carried out in a very efficient manner very early in the development process. Well, and this whole framework is now more or less readily available in order to use on one side the input of the real drive cycle, ambient conditions that might also include then road conditions and traffic conditions via the inputted drive cycles in order to then predict the electrified and hybrid vehicle overall energy efficiency, CO2 emissions, electric driving range, and much more in order to assess the performance and in order to assess electrified vehicle component technologies to decide on the sizing and dimensioning of components, of subsystems in the office, and hence to facilitate front loading of activities to earlier phases in the development process in the office itself, but also to front load activities or shift activities from the lab towards the office, and with this to considerably contribute to shortening the development process and especially also being able to cope with the increased complexity of electrified and hybrid powertrain systems in an efficient manner. Yeah, with this, I'm at the end of my presentation, and thank you very much for your interest.